So this is the sixth lecture of the series of lectures that I'm uploading about group actions. So recall that last time I talked about Mashke's theorem. What does it say? It says that any representation on finite dimensional vector space of a finite group can be written as direct sum decomposition of irreducible representations. Okay. So now remember, we are following the pathway, the exactly pathway what we followed in arbitrary group action. So there I talked about the decomposition of any group action into irreducible sub-actions. So the corresponding theorem here is the Mashke's theorem. Now, if we can recall that mm, in that case we have if we have two actions of a group on two sets, say x and y, then you have the notion of what is G invariant map between x and y. What does it say? It says that f is G invariant if uh, f of G dot x is G dot fx, where the dots are in respective uh, for respective group actions for all x in x and y in y. Okay. So similarly, if we have two representation, say one representation rho and another representation phi of a finite group. Here we are assuming G to be a finite group, okay, uh, of two vector spaces V and W respectively. Then I define a G invariant linear map, of course, because here we have vector spaces, so we have to talk about not any function but a linear map. So linear map T from V to W is said to be G invariant if so you have T from V to W. So recall rho G is a map from V to V, right? So this is a map from V to V. I can compose it with T. I will get a map from V to W, and that is same with this. And this should hold for all the group elements. Okay. And similarly, if moreover T is uh, 1 1 and on 2, then T is said to be an isomorphism between these two representations. G V and GW. Yeah. So here, let's say, so suppose let's take this. So suppose you have two representations. Uh, suppose you have two representations. One is rho from G to GLV, another one is phi from G to GLW. G is a finite group, and moreover, let's say you have a G invariant map from V to W. Okay, such that this diagram is commutative. Diagram means if you have V to V from by rho G, V to W by T, again V to W by T, and W to W by phi. So this diagram is commutative. That is what we mean when we say T is a G invariant linear map, right? And this diagram is commutative for any element. Okay. So now observe one thing that first we have the kernel of T. It is the all the elements in V that maps to 0 under T. And if you pick any element, say let me pick element x from kernel of T, then my claim is kernel of T is G invariant. that is rho g of x should again belong to kernel of t. That is equivalently t compose rho g of x is 0. But what is it? This is just phi g compose t. But anyway, t x is coming from kernel of t, so t of x is 0, so this holds. So kernel of t is a G invariant subspace of V. Subspace of V. So similarly, you have the image of t. This is a claim that image of t is also a G invariant subspace of this time W, because remember t is a map from V to W. So image lies in the W. And again, if you pick any x from image of t, this means x is nothing but t of some y in from for some y in V. Then say, remember you need to show that the image of t is G invariant subspace of W. So you need to take phi g of x, right? And this is phi g composite t of y. Again, due to commutativity, you have uh, what do we have? You have t composed with rho of g, and from there it easily follows, right? Because this is t of rho g of y. So this belongs to again image of t. So both image and kernel are G invariant subspaces of their respective domains and codomain. Okay. So then now suppose moreover that both rho and phi are irreducible. So by irreducible we mean that the only G invariant subspaces are either 0 or the entire space. So you have only two options for kernel. Either it is 0 or it is V. In this case t is 1 1, and in this case t is identically 0. Number 1. Number 2, image is either 0, in which case again t is identically 0, or sorry, image is entire W, in which case t is onto. Okay. So now the main result comes into the picture. It states that suppose you have two representation of a finite group. Suppose two irreducible representations of a finite group G, then see, then if rho and phi are not isomorphic, that means does not exist any such G invariant bijection, and by that you mean that T which commutes with every rho G and phi G, the one I defined in the beginning. So then the only possibility for T is that T is identically 0, because suppose that the suppose there exists another map uh, which is not identically 0. So then by irreducibility of phi and rho you get that T is onto as well as T is 1 1. That means T is a bijection, and anyway you have already assumed that T is a G invariant map. So any where T is G invariant. Okay. And I will call this space from V to W of all such maps by home. So this space is 0 in this case, right? And the uh, let me repeat it again, that so if t is not identically 0, that means t is 1 1 and t is on 2 by these 1 and 2, and from the fact that both kernel and image are G invariant subspaces of the respective domains and codomains. So T becomes a bijection, and we already started with T being a G invariant linear map. So we get that T is an isomorphism, but since rho and phi are not isomorphic, you get there is a contradiction. So the only possibility is T is the zero map. Okay, and okay, so now this is case one where we assume that they are not isomorphic. So now let's see what is case two we can do. See, suppose V is same as W in this. What we can do here? So again, you have the basic situation is the same. You have a G invariant map from this time V to V because we assume both are same V and W. So this is a G invariant linear map, not any map. I think I should mention here again. Yeah. So this is a G invariant map. So suppose T from V to V is a G invariant linear map where V and W are same, and again rho and rho is irreducible. Okay. So then any non-zero map is a isomorphism from these two facts. T is 1 1 and T is on 2. But we can classify all those maps because see, T is a map from V to V, and we assume that we have already assumed in the very beginning, in the last lecture I said that we always assume V is a vector space C over is a vector space over C. So and V is a finite dimensional vector space. So the characteristic polynomial is a polynomial over C, and because C is algebraically closed, it will have at least one root. Let's call that root lambda. That means there exists one lambda that is an eigenvalue, root of a characteristic polynomial of T. Yeah. But then you can consider this linear map again from V to V, and you can see that this is again a G invariant map. And so what you get is just, and I think it's easy to see this is a G invariant map because what do we need to show? This is a map from V to V, and let's compose it this and this, and you get rho g compose rho g inverse minus lambda identity because rho g and rho g inverse cancels up, but this is again T because T is G invariant. So this is another G invariant map, but this time the kernel of this map is non-trivial, or I should say it is not only 0 because there already exists the eigenvector, right, in the kernel. So by again irreducibility, this is identically 0. And what we get? We get that T is just a scalar multiple of the identity. So these type of maps are called homothetic of ratio lambda. Lambda means this scalar. So we get the only possible in this case, the home is just lambda times identity, where lambda is from C. Okay. And of course, you can take lambda to be non-zero because the zero we already assumed that T is not identically zero. But anyway, you can take that because zero map is anyway there. So this vector space is now isomorphic to C. So combining all those cases, what we get is the following. So let me write it here. So we have the cases that home this is 0 if rho is not isomorphic to phi, where rho and phi I have defined it. So let me define it again for you. And yeah, and both of them are irreducible. and if rho is equal to phi, then it is just lambda times I, where lambda are any complex number. Okay, so either it is zero dimensional space or it is isomorphic to C. Okay, so this is what's called the Schur's lemma. Okay, yeah. So now you can see one thing. So you get this lemma. This is a very fundamental and important lemma in representation theory, Schur's lemma. So uh, say the group, now you can take a particular case. I will not go in very details. I can just outline it. So you can take G to be a finite abelian group. Okay, finite abelian group. Then and fix some G in G. Okay, and you have an irreducible representation of G. Let's say then rho H uh, composed with rho G is same as rho G composed with rho H, because this is just rho Hg, but that is same as rho Gh due to commutativity, and again this due to homomorphism property. Okay. So now, so we have this fixed map rho G from V to V, right? So this is rho G is G invariant, right? So from Schur's lemma you get rho G is just scalar multiple of identity, and identity, this is a size A where n is a dimension of V. That is clear. So you can call it a corollary. So what we get is just this, and this holds for all G. So I can even take lambda G just to show the dependence on element G. So yeah, so every rho G is just scalar multiple of identity. But again, rho was chosen to be an irreducible representation. So and so the n can't be more than one, right? Because in case n is more than two, then you always have a one-dimensional fixed space or invariant subspace, right? Because these are just the identity maps. Essentially, these are identity up to some scalar multiple. So you can take the scalar outside and just take a take any v, and then rho g of v. This is just lambda g of v, which belongs to again the subspace spanned by v. So this one-dimensional subspace is G invariant, right? And then because it is irreducible, the entire this has to be the entire vector space V. So what we get is the final result that so this was any arbitrary irreducible representation of any finite abelian group, and the only possibility is then rho must be of degree 1. So any irreducible representation of a finite abelian group must be of degree 1. That is, it must be a representation, that it must be a homomorphism from G to C star. That is what we get. In case it is irreducible, of course. Otherwise, you can make any such representation from say higher dimensional vector space. Yeah. So this is just application of Schur's lemma. This is because Schur's lemma. Yeah. So this is one instance, and also. mm I can talk about another particular case about Schur's lemma, maybe one more. So in Schur's lemma, you need to have T should be a G invariant map. Then you can talk about if T is not identical to zero, then T is an isomorphism and all. But what if you have just a linear map between two vector spaces, not necessarily G invariant? Say so. Let's see. Suppose let me again change the color. So suppose T from V to W is a linear map, just a linear map, remember. So then remember that even in Mashke's theorem we choose this kind of an operator, let's see if we can do it here too. So this, this yeah. So T, so again you have two such irreducible representation, phi and rho. Okay. So phi is a map from W to W. So I think I need to switch it. Let's take rho here and phi here. Let's see. So rho g is a map from V to V, T is a map from V to W, and phi g is a map from here. And I can talk rho g inverse again. Rho g inverse is also a map from V to W, V to V, sorry. Then this is a map essentially from V to W. Yeah. And now it is easy to see that this compose, say any phi h, compose rho h inverse. This is just phi hg compose t compose rho uh, g inverse h inverse, but that is hg whole inverse, right? And you can just again change the variable, let's call it x. So that is rho x compose t compose x inverse, and here then x, then this sum will go again on this, right? So what we get is, because it's a finite group, remember, so we are just permuting among the elements. If you sum them up, the sum will be again the same. This is actually not exactly x belongs to g, or rather I should say c. So g is just xh inverse, right? Anyway, you can also take this after some suitable change of variables and all. So the sum will remain the same. Yeah. So you get t belong to this home, right? And so by Schur's lemma, you have two cases. If rho, and remember both are irreducible again, I'm not saying it. So if rho and psi are not isomorphic, then you get t tilde is 0. But let's see if both are same, then you get t tilde is some scalar multiple of identity, right? Identity of n, where n is dimension of V, which is same as again dimension of W. Okay. So now observe one thing, that uh, in this case, what is, so let's find the scalar lambda. Yeah, let's do it. So firstly, trace of t tilde, this is just same as uh, n lambda, right? So you get that lambda is trace of t tilde by n. Yeah. So then, but again, what is trace of t tilde? Remember, this case V and W are same, so both the representations are also same. So because of the property of trace function, you get this is same as trace of the linear map T. So you get just this. So eventually what you get is T tilde is nothing but a scalar multiple of identity, where this scalar is just the trace of T, where T was the map we began with by n. Yeah. So this is another simple application of uh, what is Schur's lemma. Yeah. This is, let's say, another corollary. So yeah. So remember here T was any linear map, and so one thing to note here is just any linear map can be made into a G invariant map by this by means of this. Okay, but remember you need to have G is a finite group, because then this sum will make sense. This, I mean, the finite sum. Yeah. So these are the two basic things that I wanted to talk from representation, following yesterday's mesh case theorem. Okay. So now, so let's get back into group action. So we stopped group action by saying some the class equation. Yeah. So okay. So you have that class equation from the action on G onto itself by conjugation. And there you have the fixed point set as center of G and the rest of things. Then you use the orbit stabilizer theorem on that formula and you get, yeah, the class equation. Okay. So now uh, let's see some more examples of group action. Actually, yeah. Let's see, say at least mm, 2 to 3 examples of group action. Okay. So firstly, uh, let's see some. Okay, just a sec. Yeah. Let's see some examples of group actions. Okay. So I think I gave you two main such examples. One was the one we used to prove the Lagrange's theorem, and one was the one I used to prove the that counting formula of order of the cardinality of HK. Anyway, so uh, yeah, we have this action on G cross K on H by this. Uh, uh, so what will be any orbit of any element? This will just be H G K inverse, right? And I can, right. So this is what is called the double coset. Double cos the name double coset means you are just taking sort of two side cosets, right? Double coset of G in H and K. Yeah, and mm, in case H is same as K, then your double coset will be AGH, and this is GH if H is normal. So in case of a normal subgroup, double coset and single cosets are the same. Yeah. Okay. So let's see some, say, more examples. Mm, okay. So this was number one. Number two is, suppose V is a finite dimensional vector space and consider the all subspaces of V of say any particular dimension. W is a subspace of say dimension K. So let's call this by say GK, and let's act GLV, the set of all invertible maps. So firstly, this is a well-defined action because, and what is the action? Action is just any this will send you to this. What is this? This is just A dot small w, where small w is coming from capital. This is a well-defined action because the A is a invertible map, so it will preserve the dimension. So again, AW is again a k-dimensional subspace. Okay. So the first thing is this a transitive action? That is question. And maybe I should leave these things to you. These are not very difficult to show that there is a transitive action. So the question is this transitive action? Okay. And similarly, you can do SLV. This is all those linear map, uh, all those invertible linear map which has determinant 1. Again, this will act on similar way, and the question is same: is this transitive action. Okay. So these are two main questions, and both are easy. You can think about it anyway. And let's see uh, one more application. And see here, if you can show this, then that is very easy to show because you know how to make a linear map of any, like you can normalize the determinant of any linear map. So by just take a particular column and just divide it by the determinant of that matrix, you will get a determinant 1 matrix, and you can do it. Yeah. So let me just leave it to you, these two questions. In fact, the first question will again easily imply the third, this last question. Okay. So let's see another example. So here, let's take, you have two subgroups H and K of a group G, and H is acting on the set of left cosets of K in G. By usual, you take any H, you take any G K and just act it H G K. Yeah. So what is say the stabilizer of any element? Stabilizer of say any GK. These are all elements of H such that G H G K same as GK, but that is same as uh, H in H such that G inverse this is in K, and that is all those elements of H that belongs to GK G inverse, stabilizer in H. Yeah. Okay. This is just one just easy thing to see. And okay, so now again you can, let's see one more example. I will just finish it with this example. So suppose you have a two-dimensional vector space, a dimension of V. So let's just take F2 where F is the base field, and let's take V is to be F2, and you are acting GLV on V, the usual group action. Okay. So now, so let's see, let's take G to be the GL2. Let's call it G, the group, this group. And you have the action of GL2F on F2. This is your F2. So, yeah. So firstly, let's see. Hmm, okay. So firstly, take this element. Okay, let's see. You have this unit vector, the standard ordered basis vectors, and what are the stabilizers of this vector under this action? This is easily see, these stabilizers are of this form. The first column has to be this, and these two elements can be anything. Uh, and remember the 2 entry cannot be 0 because otherwise this will be like this matrix will have determinant 0, but that is not the case because you have non-zero determinant matrices. Okay, and so this subgroup is inside the set of all upper triangular matrices. Of course, with you have to take care of this condition. Yeah. So let's call that to be B. Okay. So now, hmm, let's see. Uh, Firstly, observe that, and also you can, let's denote this matrix by W. So uh, take any vector from F2. Okay. And also observe that BE1 is just A comma 0 where A is non-zero. Okay. So take any xy from F2. If y component is uh, non-zero, or say y component is, let's take y component to be 0. Uh, okay. Then this will be just say x comma 0, right? So you can see that this belongs to say BE1 if x is non-zero. Okay. And what about this one? What is this? This is just any say if you take any um, element of B to be of this form A, B, 0, D, then this is just all those column vectors having this where D is non-zero. B can be anything. So if x is 0 in this case, then this vector xy will belong to this, right? And so this is case 1, this is case 1 under A, and this is case 1 under B. And case 2, if y is non-zero, then anyway this belongs to this set. Yeah. So you get that any vector of F2 can be written is either in B E1 or in B W E1. So F2 is union. And moreover, if you see the second component of any vector of the first set is 0, and the second component of any vector in the second set has to be non-zero. So this is just a disjoint union. Right? So F2 is a disjoint union of these two sets. Okay. And now my main claim is that the group G, that is GL2F, is, remember, B is a subgroup of G. This can be seen easily. I'm not showing. This is just B. What happened? Just a second. Yeah. So this is just B disjoint union. Uh, Wait a second. B W B, and firstly I'm leaving it to see that this is phi. That is easy to see. This is just a computation. Okay. And so take any element from G. Let's do it quickly. So G E1 is a vector in F2. So it is either in B E1 or it is in BW1, and it can't be in both of them because these are disjoint unions. So if it is in BE1, it will be some, right, for some B in B, then just B inverse G stabilizes E1, and this is again inside B. So you get G is inside B. This is case 1, and or if G E1 is inside BW E1, then it will be some BW E1 for some B in B. Then again B inverse G, B inverse omega inverse G fixes E1. So again this is inside B, and G similarly will belong to B W B. So you get a decomposition of this group into two say subsets, where the first one is a group but second one can't be a group, right, because the identity element is can be in only one of them, and because the first one, the B is a subgroup, the identity element has to belong to that set, so it can't belong to the second set. So yeah, this is just what's called the Bruhat decomposition. Okay, so let me just uh, stop this video with this corollary, and this is, you can take this as an exercise. I will talk about it in the next video. This is just, you can even do it. So the question is, if not if, I should say, B is the maximal subgroup of G. Remember, B is a subgroup. Now my claim is it is the maximal proper subgroup of G. Yeah. And by maximal I means if you take any subgroup of G which is larger than B, then it has to be the entire group. You can do it, and maybe I will talk about it in the next video. So let's just leave it as an exercise maybe, and I will talk about it in the next video. Yeah, and then I will maybe I can go into the silo theorems using group action, and then we'll talk about classification of some group. So yeah, let me just stop it here. Thanks.